In this example, we're going to approximate this definite integral, and this is a definite integral where we can't use any of the techniques we've learned so far for how to integrate, because this is one where we don't get a nice closed form for its antiderivative. So approximation is going to be our best bet here, and so we'll use the trapezoidal rule, then we'll give a bound on the error, and then we'll see how big do we need to make our n if we want our error to be less than 10 to the negative 2. Okay, so first go ahead, put this on pause, and based on what we've done in class, we'll start with part A. See if you can give me an approximation using the trapezoidal rule. Okay, so just from a picture perspective, we can remember what we're doing with this rule. If I have n as 4, then I'm trying to divide this up. So my delta x at the bottom is going to be the length of my interval, which is just 1, divided by 4. And then our trapezoidal rule, if you recall, is given by this, and we derived it in class, but the visual is again that we're going to use little trapezoids here to approximate the actual area underneath the curve. So in this particular case, we're going to have 1/2 times 1/4, and then we're going to look at our function values at each of these points. So you can think of x0 as your starting point, and my ending point is x sub 4 in this case. So if I evaluate the function when x is 0, I'm just going to get 1, and then if I do 2 times the function at 1/4, I'm going to be getting 2 times e to the 1/4 squared, which is 1/16, and you'll keep doing this until you finally look at the value of the function just when x is 1, which is just going to be e. And then if we plugged all these into a calculator, we're going to get this is approximately 1.49068. So that's our best approximation for this definite integral. Now we're going to give a bound on this error. So again, put this on pause, and then using the error bound that we gave in class, see if you can bound the error. In this problem, we're now going to estimate the error in our approximation from part A. So just so we can even understand what this notation means, this is saying I'm going to take the actual value, which I've been trying to find, and then subtract the estimate I got in part A. And in that case, I'm just going to round it to the nearest hundredth. So this is what I mean by the error. And we are going to estimate the magnitude of the error. So that's going to be putting magnitude signs on this here. And before we start with that, there's one thing that we know right away. Because this is a concave up function, e to the x squared, then we know our little trapezoids, and I'm not drawing this to scale, I'm just going to draw 2 trapezoids so you can see it a little better here. But you know that your trapezoids are going to give you an overestimate if you have a concave up function. So we actually know right away that we can write, but what we'd like to do is use my error to help me figure out a lower bound, because once I get an estimate on my error, that'll help me see how far off we are from 1.49. So let's do this now to help us get a lower bound for this. We're going to come back to this in a minute. So I'll clear some space. And now we're just going to rewrite the error estimate that we wrote in class. And again, we aren't proving this. This is out of the scope of this class to prove it. But we know that this is going to give us a bound on the error where k is determined by getting a bound on your second derivative on your interval. So notice, in order to get the smallest possible bound on my error, I'd like to pick the smallest possible k that I can. So we're going to call this, I'm going to try to get a reasonable value for k that's basically the smallest upper bound that I can find for my second derivative, because that'll help me keep my error bound small. So let's go ahead and fill in what we already know. We already know b minus a, we already know n, so we can fill that in our formula here. And now at this point we need to figure out what k is. So let's find the second derivative. So here's the first derivative and the second derivative. You're going to do the product rule. And now we're going to look at this and we're going to think of this on our interval, and I want a reasonable upper bound on my interval for this. So notice on the interval 0 to 1, this is going to be biggest when x is 1, this particular second derivative. So we can then say that the absolute value of the second derivative is going to be less than or equal to its value when x is 1. So less than or equal to, I'm just going to plug in 1 here, 4 times 1 times e to the 1 plus 2 times e to the 1, so that's 6 e, and that's what I'm going to choose for my k. Alright, so that's a reasonable upper bound. Obviously you could pick values that are bigger than 6e that would also be upper bounds, but those are no longer going to be that reasonable. The bigger that you pick your k to be, then your error bound gets worse and worse. So really you're trying to find your least upper bound that will work in the interval given. In this case that'll be 6e. So now we're going to replace that up here. And now this is going to, we'll just simplify, and this is going to give us our bound on our error. So this has to be less than e over 32, which is approximately 0.08. Okay, so if you're just asked to estimate the error, you can say the error has to be within 0.08. If you're asked to give an interval in which the actual value lies, normally you would start with the value that we got out of our estimate in part A. So you'd start with your 1.49. And then you'd say, okay, I know that my actual, this is the exact integral. And you would say, no, this has to be somewhere in between 1.49 plus or minus my error. So here's your plus 0.08 and your minus 0.08. That's what we mean by the error. But we actually know, because this was a concave up function, and we talked about this when we started, we actually know that our actual value is less than 1.49. So if we wanted to estimate the actual value of this definite integral, we know for sure it's somewhere between 1.41 and 1.49. Now, if we want to get an even better estimate, we're going to need to use more subdivisions. Instead of n being 4, we're going to use more. And so that's part C. Part C, we're going to decide in advance how small we want our error to be. This case, in part C, we want it to be 0.01, not 0.08. And we're going to see how many subdivisions we need so that we can get our error within that particular tolerance. Okay, so here, instead of knowing n, and solving for our error tolerance, now we're going to know our error tolerance and we're going to try to solve for n. So we're still going to use this, and then now I know that I want this to be less than 1/100th, and so now I'm going to fill in what I already know from the previous page about these terms. I already know k, I already know b minus a, and now I'm just going to solve this inequality for n. So notice this has got to give me, and if we plug this into a calculator, that means that this is going to give me 11.6. My n has to be greater than 11.6, so I need an actual integer value for n. So we're going to let n be greater than or equal to 12. And as soon as you do that many subdivisions, you should expect your error to be within 1/100th of the actual value. And that's it.